In this problem, it says an early major objection to the idea that the Earth is spinning on its axis was that the Earth would spin so fast at the equator, so the equator is going to be right here. It spins so fast at the equator that people would be thrown off into space. Well, if the Earth moved around like spinning a basketball on your finger, yeah, people would be thrown off into space. But it takes a whole day for the Earth to go once around. So we're not going to have enough speed where we're going to be thrown off into space. But we are still moving through a circle. Like right now, we're on the Earth. The Earth is rotating. So relative to the axis of rotation of the Earth, so a line from the North Pole to the South Pole, relative to that axis, we are moving through a circle. Now, the circle that we move through is smaller than the circle that they move through at the equator because we're not at the equator. And at the equator, that's the largest circle that we can move through using the radius of the Earth. We can figure out what ours is because we're at what, about 42 degrees north latitude? All right, that's about where we are. So knowing that number, I could actually figure out what that is. I could do this. I could say, okay, this is, if I go to 42 degrees north latitude. All right, that's probably about where we are. 42 degrees north latitude. So I know that the angle right here is 42 degrees. Because if you go straight up to the North Pole, that's at 90 degree latitude. So if you look at the latitude lines, they go from 0 up to 90. So we're at 42. So from the center of the Earth out to the surface, there's an angle of 42 degrees. And if I want to know the circle that we're moving through, all I would have to do is drop a line straight down. Oops. Drop a line straight down to there, and then this distance right here would be our radius at that location. So we'd be moving through a circle on this plane right there. So all I need to do is get that amount. Well, I can get that amount because I know the angle here is 42 degrees, and I know that's the radius of the Earth. So that's the hypotenuse, and if I know the angle and the hypotenuse, I could solve for the adjacent side, and that would be the radius of the circle that we're moving through. But they made the problem simpler than that. We're not looking at 42 degrees north latitude. We're looking at the equator. So the radius of the circle for anybody at the equator is going to be the radius of the Earth. So that's our problem. Now, so what I'm going to do here is I'm going to put a person at the equator. So here's a person at the equator. Now, when we've done problems where we just said, well, what would be the forces if we had a horizontal surface and we had a person on that surface, and if I asked you, what are the two forces that are acting on that person? Like right now, I'm standing here. What are the two forces that are acting on my body right now? Gravity, so my weight, right? So I would have my weight down. And if that was the only force on me, I would right now be falling at 9.8 meters per second squared. So what's the other force? What? The normal force. So the normal force is in that direction. And what we did before we factored in that we're on a planet that's moving, we would say that our weight is equal to our normal force. And for, that's pretty much how you do it on a small scale. I'm just looking at the, I'm stationary relative to this room. Relative to the axis of the Earth, I'm moving because the Earth is rotating. But relative to this room, I'm not moving. So I've got the weight down and I've got the normal force up, and they balance out, right? But if we look at it from the perspective of a person on the Earth that's moving through a circle, then these same forces are going to be on this person. So I'm going to have the weight in that direction, and I'm going to have the normal force in that direction. Now, if you look at the length, the way I drew these, so there's the weight, and there's the normal force. If you look at the way I drew them, I drew the weight arrow a little bit longer than I drew the normal force arrow, because this person is going to move in a circle. They're going to move through a circle. So if they're going to move through a circle, then there has to be a net force towards the center of the circle, because this person is constantly changing direction. If these two are equal, this person would come right out of the board. So I have to have more weight than normal force. Now the question asks me to solve for the apparent weight. It says, what's the apparent weight of a 100-kilogram person at the equator? The apparent weight is what the normal force is, because if I was standing on a scale, that's what it's going to read. We did the same thing when we had this. Remember when we had, like if you were in an elevator, and if the elevator was accelerating upward, that number had to be bigger than that. If the elevator was accelerating downward, that number had to be bigger than that one. So we've already done it where the normal force did not necessarily equal the weight. In that example, it was accelerating because the speed was changing. In this example, it's accelerating because the direction is changing. So there's my picture. So once I have the picture, let me get this out of the way so I have room to do the work. I'm going to write my descriptive equation. So who can tell me, if this is my picture, how would I describe that as an equation? What would it be? Now remember, forces towards the center of the circle are positive centripetal forces, and forces away are negative centripetal forces. So what would be my descriptive equation in this example? Let's right, W minus Fn equals, now it's going to equal either mv squared over r or mr omega squared. If the unknown in the problem was the r, I would put mr omega squared. If I knew the angular velocity of the Earth's rotation in radians per second, I would use mr omega squared. But if those two situations do not apply to this problem, I would prefer to use mv squared over r. Anytime I can avoid the radian unit, I'm going to avoid the radian unit. Now, the weight, it's a 100-kilogram person. So, a 100-kilogram person, W equals mg. So, what would the weight be of this person? The true weight. What? If I have a 100-kilogram person, what will their weight be? You should be able to do that in your head. 980. Because 100 times 9.8 is 980. So this person's weight would be 980 newtons. So this number is going to have to be less than that, because I need some sort of force that's going to allow the person to move through a circle. And it's a pretty big circle when you think about it. I mean, if you had to go around the Earth in one day, even though it's one day, you'd have to be moving pretty fast. I mean, it takes 3 days to get from Massachusetts to California. If you drive almost the whole way without any stops, it takes about 3 days. So you got to be moving pretty fast if you're going to move through the circumference of the Earth in one day. And we could we'll figure that out in a second. We'll figure out what the velocity is of the person. But if you look in the problem, what we do know is we have the weight. We have enough information to get the weight because we have the mass, and gravity's 9.8 meters per second squared. We have, okay, now the radius is going to be the radius of the Earth, so we can have that. We know the mass of the person, so I do need to calculate V. So let's do that first. Let's see actually how fast you'd be moving in this problem. So my starting point is how fast does the Earth rotate? Does one rotation every what? 24 hours. So if the Earth is rotating once every 24 hours and I'm on the Earth's surface, then I'm revolving around the Earth one revolution every 24 hours. So 1 rev every 24 hours. And I can convert it into meters per second in 2 steps, because I can convert my revolutions into meters, and I can convert my hours into seconds. So I'm going to get 1 revolution equals, again, if we're doing a circle, we're moving through the circumference of a circle. So it's going to be 2 pi times the radius of the Earth. It's on your formula fact sheet. The radius of the Earth is 6.38 times 10 to the 6th meters. So that's the radius of the Earth. And in 1 hour, how many seconds are in 1 hour? What? 3,600. So solving for V, figure that out. That'll be the velocity in meters per second, which I don't know whether, whether you'd be able to visualize what that would be. I mean, I could convert it into miles per hour to give you an idea, but for now, let's just get the answer meters per second. After we're done, maybe I'll solve it so you can see, because most of us have a better idea, a better grasp of the answer for speed if it was in miles per hour instead of meters per second. But let's see what we get. I get 463.96 or 464. So 464 meters per second. So now that I know the V, I can just plug all those numbers into my, well, again, the unknown in the problem is the apparent weight. So I do need to rearrange this equation to get Fn by itself. Now, since Fn is negative, I'm going to move it to the other side, and I'm going to move this to that side. So when I'm done, I'm going to get that the normal force, which would represent the apparent weight, what the scale would read if I was standing on a scale, the normal force is going to equal the weight minus mv squared over r. So somewhere over here, you should probably calculate W. W is mg. So it's going to be 100 kilograms times 9.8 meters per second squared. So that's going to equal 980 newtons. So now I have all the numbers that I need to calculate the apparent weight. So plugging in these numbers, I'm going to get Fn equals W minus mv squared divided by r. I'm going to make the r big because I'm putting the radius of the Earth, which is in scientific notation. So the weight is 980 newtons. The mass of the person is 100 kilograms. The velocity is 464 meters per second. And the radius is 6.38 times 10 to the 6th meters. And I will get newtons. This is newtons, and this will all be newtons, because I have kilogram meters squared per second squared divided by meters. So I'll end up getting kilogram meter per second squared, which is a newton. So I'll be subtracting newton from newtons, and that's going to give me the answer here, which, like I said, I think this part right here works out to be like 3.4 newtons. So if I subtract 3.4 from 980, I get 976.6 newtons. And if I round that to 3 significant digits, you get 977 newtons.